In this video we're talking about the central limit theorem. This sort of builds upon the last video about sampling distributions, so if you haven't already seen that one, I would take a look at that first. The central limit theorem is a really important theorem in statistics. In math, theorem just means sort of something that can be proven to be true, some important result. So the central limit theorem looks at when we're looking at multiple samples, all of the same size, so the samples are all supposed to be size n, and in our textbook we assume that n is at least 30, right, or bigger than 30, so this doesn't really work as well with very small samples. In practice, most samples are, much larger than this, but it's something we have to be concerned about. So if we take multiple samples of the same size that aren't too small, then x bar, remember this is the mean of the samples, this will be normally distributed with mean the same as the population mean, mu. The notation that they use in this particular textbook is the mu notation for x bar. So x bar is a little subscript here, looking at the distribution of all of the sample means. That mean is the population mean, and the standard deviation for this normal distribution is the population standard deviation divided by the square root of the size of the of the size of the sample. So you can imagine if you have a very large sample, then this standard deviation here would be dividing by a real big number, and the standard deviation would be very small. So in practice, that means that if you take very large sample sizes and find the mean, your mean is going to be very close to the population mean because it doesn't vary by very much, right, if we have a small standard deviation. So the big key importance here is that this sample mean is going to be normally distributed even if your normal data is not normally distributed. So for any type of data, this is true. And that's why it's so important, is that it becomes very valuable when you deal with data that isn't normally distributed. One thing that our book doesn't make super clear in their statement of the theorem is that, for one thing, this theorem is true even if the population is not normally distributed. But if our regular data is normally distributed, then we don't need the restriction that n has to be large. So if you already have normal data, normally distributed data, then you don't have to worry about the size. The size is only going to be really important when your data is not normal or not very close to normal. So to understand what this is really saying, let's look at an example. So here we're looking at a ski gondola. Its capacity is to hold 12 people, but if the weights of these people average more than 170 pounds, then the weight capacity of the gondola is exceeded. So we're looking at weights, and we're going to look at weights of men here, just because men tend to be heavier, so we're going to take women out of the equation. The weights of men are normally distributed with a mean value of 183 pounds and a standard deviation of 41 pounds. And this is just some basic data that you would be given in the problem. The first part of this question asks us to find the probability that one single man that we select at random will have a weight more than 170 pounds. Now this problem is just a regular normal distribution problem. We're looking at some normally distributed weights, right? Again, I like to draw a picture here. We've got the weights of men are sort of centered around 183 pounds. And our standard deviation is 41 pounds. And we want to know what's the probability that a randomly selected person would have weight more than 170. Well, if I draw 170 on here, that's less than the mean. So 170 is somewhere over here. So we want to find this area under the normal curve, or this probability to the right of 170. So we've looked at this in a previous video. We first have to find the z-score associated with 170. So that would be our 170 minus the mean divided by our standard deviation. In this case, this comes out to negative 0.32 if we round to 2 decimal places. This is negative because it's on the left-hand side of the mean, so we should expect to see that. And then we're going to have to look up in our z-score chart, what this area is. Now remember, the areas in the z-score chart are always the area to the left. So when we look up z equals negative 0.32 in the chart, we're actually going to get this area over on the left here. So the area from the chart was 0.3745. And then to get this other area on the right, which is the one that we actually want, we just have to do 1 minus that. So we get 0.6255, or we could think of this as about 63% chance. So about 63% of men have weights more than 170 pounds. If we think about this gondola problem, we already know that there's going to be a problem here. If, more than half or significantly more than half of men have a weight over 170 pounds, then there's a pretty good chance that when you load 12 men on the gondola that you're going to have a problem. But this computation that we just did is really just looking at one single man. It doesn't look at what's going to happen when we take 12 men at once. To do that, we're going to have to treat this as a sample. So we're imagining picking 12 men, right? We've got a sample with size 12 selected randomly, and we want to know the probability again that the weight is more than 170 pounds. Now, what the central limit theorem tells us is that the sample means will be normally distributed, with the mean of those samples being the same as the mean of the population, which in this case was 183. But the standard deviation of these sample means will be the population standard deviation over root n. So in this case, our population standard deviation was 41 pounds, and n is 12, so we get 41 divided by root 12. And if we compute this out, this comes out to about 11.836. So, same kind of process here, we just have a slightly different distribution. We're still looking at 170 pounds, which will be somewhere on the left. We're going to have to compute a z-score for the 170 pounds, but now our mean is 183, and our standard deviation is much smaller here. And this shouldn't be too surprising that the standard deviation is smaller, because the weight of one particular person is likely to spread out more than if we have a group of 12. When we look at the group of 12, you might have some heavier people and some lighter people, but they average out a little bit more. So the mean of our sample is going to be closer in towards 183 than the means of just a single person. And that's sort of what the central limit theorem tells us. One additional note, in the central limit theorem, if I scooch back up, it did say that our n had to be greater than 30, which is not the case in this problem that we're working right here. Right here we only have 12, right? Only 12 people that we're selecting. However, that note that I put in here said that if the population is actually normally distributed by itself, then you don't need that requirement. So because this problem told us that the weights of men were already normally distributed, we don't have to worry about that size. Okay, so we compute our z-score here. If we round this, this comes out to negative 1.10. And again, when we look this up in the table, we're going to get this area to the left, but what we actually want is the area to the right, right? The probability that the sample average is more than 170 pounds. So this is what we want. So our number from the table comes out to 0.1357, which makes the area that we want 0.8643. So if we convert this to a probability, this is just 0.8643. As a percentage, this would be 86%. So if we compare these answers, we said that the probability that one particular person has a weight more than 170 pounds is about 63%, but the probability that among 12 men that the average would be more than 170 is 86%. 86% of the time, 12 men will exceed the weight capacity of this gondola. So this calculation would change if we were going to include women and children and things like that, but this means that there's probably something wrong with this capacity, right? Either the weight capacity is too low or they shouldn't be letting so many people on. So when you do these calculations, make sure you're paying attention to whether you're just talking about selecting one single person or one single data value versus selecting a whole sample of them. Right? If we're selecting a sample, then we're using our central limit theorem to get sort of an alternate distribution. So here's a problem for you to try. That's it for this video.